Anyway, so welcome to the tutorial on atom probe data visualization analysis with Blender and Matlab. So this tutorial was initialized by Sarita and Josh, who work on interfacial access mapping, and they wanted a tutorial on the stuff that I've done so far with Matlab and Blender, which they are using and sometimes battling with, and sometimes getting along a bit better. And so this is going to be a 2-hour tutorial. I don't know because of the fire alarm we got cut a bit short, but I'm still trying to cover as much as I can. Um, but anyway, so what the great, does that? No, that's not really good for the recording. So what we're going to cover is first Blender basics, which is just showing you how to do some basic visualization, which is pretty much something that everyone that does atom probe can use to make their data publishable, or make the visualization a publishable quality. This is just an overview of Blender, how to use it, and what the basic things is you need to do. Importing atom probe data, how we're going to do that. Visualization. So visualization just means how do you set up a proper scene that you can get an image of your data set out of. And animation basics. Animation basics is just how to create a 360-degree turntable animation, which you see very, very regularly on in atom probe data in different presentations. Just everyone probably knows it from Iris, where you just click, you do a movie and it does that. Of course, with Blender you can go as fancy as you like, but we'll just stick with the basics. And then for the second hour, I had planned the basics of interface analysis. So we're not going to go into dislocations, clusters, or anything else. Just interfaces. What are the basic principles? How do you actually get your objects out there? Which is decom, which works for grain boundaries and things like that, and dislocations and alike. And margin cubes, which is isosurfaces, just like we've been using them in atom probe for a long, long time. How to calculate a proximity histogram from an object. How to calculate a single interfacial access value, so you get one single value for the entire interface. And then finally, I hope we'll get to do some interfacial access mapping at the end. So let's get started with Blender. And so Blender is from the Blender Foundation. They sit in Holland, in Amsterdam. They've got quite a few people working on that. So always try to keep up to date, because the versions change and the capabilities of the program change. So if you can, try to stay on top of that. And the resources you need for that, I'm actually gonna put the presentation up as well, so you've got all the links and everything. So the resources you need is blender.org. That's the page of the page of the organization itself, where you can download Blender. And I should also add Blender Nation, which is the big community page, where you'll find a lot of what's going on in community and related CG computer graphics things. BlendSwap, if you wanna download some models of something that you want to use for visualizations. It's just a repository. They've got good materials there as well. I'll show you later what that means. And most importantly, when you're starting out, tutorials. So if you go on cgcookie.com Blender, they've got very good basic tutorials where you can learn how to use Blender properly, because of course we're not going to go into depth today. And blenderguru.com is another good tutorials page. And if you need to look up file formats, so the file formats we're mostly going to use are .obj and .ply. And the .obj we're going to use for everything that's just a mesh, which means just an interface or something like that, because it only consists out of vertices and triangles. And we're going to use .ply, which is standard ply file format, for anything that has any result data tied to it. So a finished interfacial access map will be a PLY, because when you visualize it, it has some color data which represents the interfacial access associated with it. So the file formats, why do we need different file formats? In the APT software, There's formats like .pos, .epos, .ato, and I'm pretty sure the guys in Stuttgart have their own file format, which is specific to the AtomProp software. So .pos, the most common one, is X, Y, Z, and master charge, all in binary file formats. And a CG software can read binary file formats, but for today we're going to use .obj, which is an ASCII. It's a text format, and it has X, Y, Z. I'll just show you what one looks like. OBJ, just some random. So that's an OBJ that's created by one of my exporters, and you can see it's just the different vertices of the mesh here, and eventually you get a list of triangles. And for all of the files that we're going to use, there needs to be an O between the V's and the F's. What that means is it designates that there's an object coming. That's not actually something that's specified in the file specification, but in all the files that we're going to use, it needs to be there, because otherwise the programs will get confused. Sarita had the problem last week where she had files that were exported from Blender that didn't have the O in it, and so she had problems reading them. And at the end, there might be other things like material libraries and other stuff, but that's of course things that we don't need because we're only doing meshes. All right, so let's get straight into the fun. While we're doing this, because we've got lots of different freedom, and we've got different rendering options. So all of the other AtomProp programs, they are geared to do both visualization and final rendering. So real-time visualization, final rendering, with the same render engine, which in Iris I think is a software renderer, and in 3Dpic is OpenGL. But of course that sets some limitations in terms of what you can do. In Blender we've got a couple of different internal ones. So we've got Freestyle, which is a stroke renderer, which means it can paint strokes. In the near future it will also be able to produce vector graphics. So you'd be able to render your AtomProp data to vector graphics, and that's going to be a big upside. The Blender internal one is a so-called scanlight renderer. Doesn't matter what that is, and cycles the ray tracer. So the difference between those two is with the Blender internal, you can fake a lot more stuff. With the ray tracer, it looks realistic and very plastic straight away. But usually we're trying to stay on this side these days because it's much easier to work with, much easier to set up, and you don't need to understand much about what you're doing. And of course, you can go pretty fancy and, for example, render your clusters as, I don't know, something creative. All right, let's get cracking with Blender. So everyone open their copy, and so the first thing is you need to be able to do the 3D navigation. And middle mouse button is rotation. The mouse wheel is zooming, and shift middle mouse button is panning. If you're in a Mac and it doesn't work that way, then go into user preferences and input, and click emulate three button mouse. If you're on a PC, you've got the 3-button mouse anyway, so you don't need that. So is everyone try to zoom around, pan around a little bit? So one of the important things when you're working with Blender is you really need a keyboard and you really need a mouse. Don't do it just on your laptop. It's gonna be a massive pain in the ass. I do it occasionally if I'm on the go, but I avoid it whenever I can. One of the main reasons is because you've got the number pad. So you can see I've got the screencast keys on. So whenever I press a key, you're going to be able to see the key that I'm pressing here, right? And with the screencast key, with the number pad, you're able to switch to different views, and most of all switch between camera view and whatever view you had before, but just by pressing number pad 0. And that's an important thing because you want to check what the camera position is very often. So just to give you a basic outline of the fields that we have in Blender, the first one is the 3D view here. That's where you're going to see all your scene data, so that's where you're going to see all your objects. The second one is the outliner here. That's where you see, that's where the object information is. So you can click on stuff here as well. So you can see the lamp, the cube, the camera. You can access them here. And any data associated with it will also be accessible here. Don't worry what the scene and the render layers and the world and everything means. We're not going to be working with that. And everything where you're doing something or everything that's associated with objects or with whatever your data is here. So the most basic one would just be, the first thing, just click on render. And if you click on render on your standard scene, you should see exactly that default cube rendered out. And also it switched the 3D view to the image editor, because of course the render output is a 2D output, and that's why it's switched here. And if you press escape again, you'll come back to your scene. And the fourth part of a window that we have down here, that's a timeline, and that's what we're gonna need when we're doing animation. So as now we're scrolling through the animation, but there is no animation, so nothing's happening. But we can actually forget about that for now. So I'll just make it all 3D view. And this is the most basic navigation. In terms of the tabs, so what do we have here? The first one is the scene tab or the render tab, where we can either render just one frame or we can render the entire animation. Again, we'll come back to animation later. Resolution presets, you can come up with your own render presets. The one I'm usually using is, I call it 1024. It's 1024 by 1024, so it's a square format. And you can see the camera has changed. The camera outline has changed now. It's square. It was rectangular before. And it renders out at 50%. So if I click render now, this is actually 512 by 512. So that just has the purpose that you can do quick renders and check whatever you're doing, and then later come back and just crank it up to 100% and do your final render. Because render times can get pretty long, so you don't always want to render at full resolution. Even though with the techniques that we're going to be using, we're going to probably keep our render times below in the seconds range. But if you go very fancy, it can be minutes. I've had renders that took hours. So 1024 by 1024, because it's a power of 2. Try to stick with power of 2s. It makes working with the images later easier. Unless you're actually doing rendering for specific screens. So you might be rendering for HDTV, so that's 1080p or 720p or whatever, because that's a projector or whatever device you'd be working with. But for our purpose, mostly 1024 by 1024 or 1024 by 2048. That's fairly high resolution, so there's I very often do lower resolution renders for publications, because if it's a 2, 3, 4 centimeter figure, doesn't make sense to render out at that high resolution. Then forget about that's not as important for you. With the shading, there's one very important thing, and that's alpha. So alpha is a transparency channel, and it's right now set to sky. So if I go and render, you'll see I have a gray background, because if I go into the world, gray is the sky. But mostly when we're working with edit and prop data, we want it to be transparent. And if I now render out, you'll see there's no background. So that the checkout thing means no background. And the reason is when you're making a figure later in Illustrator, you have an alpha channel and you can have overlapping objects. So just imagine you've got a render where one corner is empty. You can move things above each other and they're not going to block each other out, because there's just transparency there. Performance. When you do very long renders, that comes into play, and you'll just go and crank your threads down so that you can go and keep working with your computer while 6 of your 8 cores or 3 of your 4 cores render, and you use the remaining core to do whatever work you're doing. Post-processing, it's not as important. Freestyle, so that's a stroke renderer. We're gonna talk about that one a little bit later because it's actually really handy for add-on probe visualization. And stamps, if you do trial renders, just put timestamps on there so that you remember where you put stuff. In the output, that's just where it's gonna render. I always render to the default temporary folder so that if I forget to delete old renders that I didn't use anyway, then the system will go and delete them. So that's why I just render. And then the last important choice is what sort of file format we're rendering out to. PNG is it's going to be different from movies or images. And usually we either render out to PNG or TIFF, mostly PNG, occasionally JPEGs, and when it comes to movies, MPEG or QuickTime. But when you're rendering an animation, unless you're really sure about it, if it's a simple turntable animation, render it straight to a movie format. If you're doing a really complicated animation, render it out to images and then turn your images into a movie. Because if your render dies if your computer craps out or dies during the rendering, which occasionally happens, you've lost all your work. If you render it out to images, you just start where you left off and keep rendering. And then it eventually delete it. Color depth, 8-bit colors work well. I had problems with the 16-bit colors. I don't know why. And with the colors, you've got black and white, RGB, or RGB alpha. So if you have transparency in your image, which we usually do have, we use RGB alpha. Otherwise, use RGB or black and white. It will actually make your image smaller. I try to sometimes keep my animations in black and white because it makes the animation a lot smaller. It makes the files in the end a lot smaller. We're not going to be using baking. Then render layers. We're not going to use render layers, and I'll show you later how Freestyle works. In the world, the important things are global lighting. So the world means what's the environment that we're using in Blender, and that's mostly the lighting. And there's 3 types of lighting: ambient occlusion, environment lighting, and indirect lighting. And what they mean is ambient occlusion means that you're calculating lighting based on distance. So if you just look around in the room, you can always see that if wherever there's geometry that's a bit closer to each other, then it's a little bit darker. Like if you look into a corner is always darker than somewhere where there's no corner. So I'll just show you what ambient occlusion. So ambient occlusion, so this is all without any lighting, but you can easily see here in this image that you have wherever, oh no, this is actually including lighting. This is because there's a shadow, so there must be some lighting somewhere. But this is just ambient occlusion. So what that means is if you've got corners or crevices, it goes darker, and if you've got open surfaces, it goes brighter. Anyway, so just to give you an impression of what ambient occlusion does. And you can multiply or add the ambient occlusion. And usually you have to try whatever you like more. I will see later. Environment lighting just means that there's a global light coming onto your surface. And indirect lighting means that you get light bounces. We're not going to use that. And then when you switch it on, you get your properties, and the properties are pretty much how many light bounces it calculates and how many samples for the light bounces. So if you use ambient occlusion and your image looks a bit noisy, the samples is what you need to crank up, probably to either 12 or 24. Then here we've got the object data. The most important thing about the object data is, of course, the name. So name your objects in a sensible way, so that if you give your file to someone else, they can make sense of what the object name actually means. Then just the basic properties: location, rotation, scale of the objects in whatever mode you want to have it. Most people here, I think, like Euler. Mathematically, it's easiest to use quaternions or axis angle. Then you can lock certain properties in case of in case you don't want to accidentally click and move your object, which atom prop data you shouldn't move anyway because the data should stay as it is. Which layers it belongs to, so each object can belong to different layers. And if you just use the normal numbers on your keyboard, then it moves from and press M. So if the normal numbers are actually, so we're going through the different layers. You can see the layers here. Right now, all of our objects are on layer 1, but there's 20 layers, and you can move your objects around. So if you've got complicated visualizations, you might want to have, so say you've got 5 different elements, and you want to render out each element. What you would do is you would set up your scene with whatever element you start with. You render that out, and you have all your other elements, all your other element atomic distributions on different layers. And then you always move the one that you want to visualize on the first layer, on the layer where you have your visualization set up, and render it out. And that's how everything in your scene stays neat and tidy. Groups, we're not going to work with groups. Display is sometimes very important because we usually use the hull of the atom prop dataset. And if you visualize the hull of the atom prop dataset as a full object, they can't see anything else. So usually you just set it to maximum draw type wire, and then no matter what sort of draw type you choose for all the other objects, it's always just going to be a wire. And you can force other things to be drawn as well. Sometimes it makes sense to draw the name and the wire, but the wire is chosen now anyway. And draw all edges, especially if you work with analysis meshes, because otherwise you might look at your mesh and wonder why there's an edge missing and it's just not drawn. And the most important thing for visualization we're going to have on this tab here is duplication. So what that means is that for whatever object you have, you can duplicate other objects on the vertices of that object or on the faces or other properties. So what we're going to do is we're going to load in our atom probe data as a mesh with only vertices. Then we're going to create one sphere that's going to represent the atom, and we're going to vertex duplicate that sphere. And that's how we do the visualization if we use spheres. And that's it. That's a more higher quality rendering type of atoms. And I'll show you another one as well. Constraints, we're gonna not use that very much. We'll come to it later. Modifiers, what modifiers do is they take a certain mesh and turn it into a different mesh. And that obviously we're not doing it with atom probe data itself, but we're going to use it for some visualization purposes. You can see there's quite a few of those. But one thing that helps us a lot is if we want, for example, a bounding box for our atom probe visualization, we will use the wireframe modifier to just take a cube and turn it into sort of a wireframe cube. And the other one we're definitely going to use is a subdivision surface. So this is the first order subdivision surface of a cube. Just smoothes things out. Second order. So it just gives your render, or it just gives your object a smoother quality. If you use Catmull-Clark, so that's a Catmull-Clark is a regional Bezier spline approximation, or the other one is just simple. So if you go into Y, you can see, right? So we're just increasing the subdivisions of the mesh. Oh, so I've pressed Z. So Z gets you between wireframe view and solid view. Then I'll come to that later. And materials is one of the other very, very important things we're going to be working with. So think of a material as the color of your object. It does, of course, more than just coloring the object, but that's the color of your object. And note we're still working with, so this is what the different renderers are, and we'll keep working with the Blender render, so the internal render engine. We'll use Blender render, and we're gonna use OpenGL directly, so we can just render out whatever is in your viewport. So if you go OpenGL render image, it just renders whatever is in your viewport exactly the way it is there, and very often that does the job very, very well. Better than you might be setting up your scene. So these days I even use it for production renders. That said, it will not have anti-aliasing, which means it's going to have those little jagged edges. So if we go to that cube, for example, it's got a material associated with it already. So we'd call it cube material, for example. And if we want to give the cube a color, we'll make it red maybe. And if I go and render it now, you'll see we've got a red cube, right? So the material is pretty much the color of your object. And of course, there's different properties. So it has a diffuse color, it's got a specular color, which means it's the sort of glossy highlights it has. And it can also emit light and so on and so forth, or it can have transparency. That's sometimes important for if you've got things that are occluding each other. But for the beginning, what we're going to be working with is actually shadeless material. So if you click on shadeless, a lot of the options disappear, which means it doesn't react to lighting. It just comes off as a color that you've set it to, which of course means it doesn't look very plastic anymore. But a lot of the renders that I do these days are not actually based on lighting as much. But I mentioned the method, the renderer called Freestyle. So if I switch that on, you can see now we've got this comic-like stylized cube. And that's actually very good for scientific visualizations. It looks like a pretty good high-quality visualization straight away. So if you just go into your Blender, try to change your material to some color, and click on Freestyle, and then render it out. Then you should all get an image kind of like the one that I have here. Which part? How do you render it? You just click on render. So give it a you say go into the materials tab. If it doesn't have a material, you click on plus. Then you change the diffuse color to whatever you like. You can pick whatever color you like. And then you click shadeless. So we're not doing any shading on it. Shadeless is under the shading tab. And then you render it out. And the first time if you render it out just shadeless without anything else, you'd get something that doesn't look very plastic. No, Anna, you did an OpenGL render?
Which render should I be doing?
Just a normal one. Just the one in the first tab, in the tab with the little camera on it. If you scroll down a little bit here, there's one tab called Freestyle, and you just click on it. And with Freestyle, you actually get your Freestyle options in a second tab, in the Scene tab. So you can see there's different options of line sets. So right now we've just got the visible line set on. So all of the visible lines, including silhouettes, borders, and creases, are rendered as a solid 1-point line, or whatever it was set to at 1 or 2 point.
Yeah, I can't do anything either.
I can't do anything in Freestyle.
Oh, you need to check box it.
You need to check the Freestyle box.
Oh my god.
And if you... So you can have more than one line style set, and if you, because sometimes we want to render hidden lines as well. So I just show you, if you want to have more than one line set, you just add another line set. Might call it hidden. Go to hidden. So QI range just means occlusion range. Visible means the first layer that the camera sees. Hidden means, I think, everything from the second layer on that the camera sees. And QI range means you can have, I don't know, the second occluded layer until the fifth occluded layer. But now we just go for hidden and make the hidden lines dash dotted. So 4, 2, or 5, 3, or whatever. If you go render now, you can see we've got the hidden parts of the cube as well. Don't worry about the line sets. If you would really need to work with that, you'll go back into the video and have a look. All right, so everyone's gotten their first render now, I suppose. Which means what?
Yeah, mine for color hasn't changed.
Because
I added a new
you need to delete the first material.
How? Yeah, you can. It will only render the first material because the first material is applied to the entire cube. The reason why you can have multiple materials is because on one object you can have parts of one object with one material and parts with another material. And if you had a default material and you added another material, then it will still render with the default material, which means your gray cube.
Yeah, okay. So how do I make it shadeless? Is it default?
Yeah, I mean it's optional, but that's what we did. And you're not gonna see any ambient occlusion because there's no concave areas in the model that we had here, so there's nothing that's being occluded, and that's why I don't see any shading based on that.
What did I do?
How did you make the hidden lines dotted?
Don't worry about that. We want to go and have a look at the atom prop stuff. This is just the basics. You can go back into the recording and have a look at that. The next very important thing, and that's something you're going to be working with a lot, is edit mode. So everything we did up to now is in object mode. So you can see the different modes here. And we're going to have edit mode and object mode. So edit mode, object mode, as it was now, means whenever you do something, you do it to the entire object. But every object is actually a mesh. So it consists out of vertices and polygons. And there's the very first thing that's actually different between what's in here and what we are going to be working with, because Blender or most CG software can actually work with triangles, quadrilaterals, and polygons. Everything we do is just going to be triangles. So always make sure that your surface is going to be fully triangulated when you're going to be using it for analysis. The reason for that is that only a fully triangulated surface is an unambiguous surface. If you have quadrilaterals, in the end, if you create a mesh from or if you calculate something from the mesh, you always need to work with triangles, which means you need to triangulate the quadrilaterals, and they can always be triangulated in two different ways, and we can't have this ambiguity. That's why we always need to be sure that everything we do is completely quadrilaterals, completely triangulated. And when we work with the mesh, so if you hit the numpad slash, you actually can get in the local view, which means you only see the object you're working with. So you can see local global view. And you hit the tab key, or you go here into edit mode. So you can tab in and tab out, right? Then you start seeing the mesh. Of course, it's a cube, which means it consists out of quadrilaterals. We want to turn them into triangles. Just go, Control T. And they're all triangles now. And what you do in edit mode is you edit the mesh directly. So I can, for example, click on a vertex here, go G for grab, and deform the cube however I want. Right? And that's the...
Manipulating the data.
Well, you shouldn't be manipulating your atom probe data. Even though you can do whatever you want with the atom probe data, that would actually be fraudulent use of your data, and I highly do not recommend you to do that.
Question: is there any other command for to triangulate it? Because
Nope.
The Alt T doesn't seem to be working.
Control T.
There's like the option.
So, that brings us actually to one very important feature of Blender, and that's Spacebar. So whenever you know what a command's called, and or you sort of know what it's called, hit Spacebar, and then triangulate faces. Okay, and then type in whatever you think it's called, and it will eventually come up with the command, right? So that's one very important thing. It's not like I know all of the commands off the top of my head. Some of them are hidden in the menus. Some of them don't have shortcuts. But
What do you do after you click on triangulate faces? What do you do then?
what? That was just to.
The object?
Yeah, you have to have the vertices selected. We don't have them selected anymore. And that's the most simple way of manipulating your vertices. Just G. I'm not going to go into the details of modeling because that's where there's other tutorials on the web that are probably better than whatever I can tell you. I just wanted to show you the basics so that later you're not going to be confused when I'm going to be doing things. Anyway, so we've got object and edit mode. So let's get cracking with some atom prop data. So get out of the local view. And I'm going to get rid of we're going to work without lighting in this case. And we're going to get rid of the cube because that's not actually atom prop data. So first thing is I'm going to later show you how to create the OBJs. But since we're now in the workflow with Blender already, we'll just load in some data. So if you go onto File, Import, you'll see the different file formats you can import. There's other plugins as well. But mostly these are the important ones. And again, we're going to be using PLYs and we're going to be using OBJs. And we're going to start with an OBJ. And when we load in the OBJ, we'll get some options here. And the important options for us are keep vertex order, because otherwise this program is made to deal with meshes and not with point cloud data. And if we don't keep vertex order, it will only keep the vertices that belong to triangles, which in our case are none at all, because we're loading in point cloud data. So you click keep vertex order, and you can either use the coordinate system as it is here, but that makes navigation a bit of a pain in the butt. So usually I use as the forward direction X, and as the up direction -Z. And I don't know what do we have, and then I'll just choose some data. What do we have here? Subvolume, example volume, OBJ export, example. That looks like Ginny's data. So that's some carbon around a grain boundary, if I remember right. I'll just import that and we'll see. Yeah, that's not a lot of data. So that's the clipped volume. Sorry, I'll delete that. I'll get in. So one thing you'll notice is now that I run it again, it's still stuck to the same settings here. But you'll need to do that whenever you launch Blender again. Yeah, your data is not split up. Okay, let's go into Matlab and actually create the OBJs. So the other stuff that's in what? No, you're supposed to create the OBJ files now. That's part of the exercise. All right, hello Matlab. Okay, Matlab's died. So I'll just go in my folder, and in one way I've got the post tools, and I can show you how to do it fully automated. What? To one that says general, the one that says general, resources, post tools. and that's just showing you how to. I'm just showing people how to get stuff into Matlab first, and then we'll just do the fully automated one, because otherwise it's boring. Anyway, so if you load it into Matlab by if you see that you've got the read pos and save pos utilities here, or epos, just go pos equals read pos. It will come up with a dialog. And Atom Pro Blender Workshop, example data. And there we go. So you'll see here you've got everything loaded in. And you've got X, Y, Z and master charge. This is a super alloy, so you'll find a lot of values around 25-ish. That's of course the raw data. Raw data means we haven't pulled out what's carbon, what's iron, what's whatever. But one simple thing would be to say, I don't know, we know that carbon is a peak around 6. So of course we would do that for every single range. If we do it by hand, then we'd say carbon is the pos file, and out of the pos file, it's everything where the fourth column of the pos file is less than 6, let's say 6.5, and everything in the fourth column of the pos file is also larger than 5.5. So there's everything around 6, right? And we want all 4 columns of that. And don't forget to hit the semicolon at the end, otherwise it's going to print a lot of... My bad. Now I can see we've got 415 C atoms, and we can scatter plot them. Come on, it must be... Oh yeah, I've got one where I've used carbon. And now we've got the rotation on, so you can see we've got a grain boundary with a little bit of carbon in there. Since it's only about 400 atoms, that's very easy to visualize it in Matlab, and it's CP and everything. If you want to do that with some tens of thousands of atoms in Matlab, it's not going to be very CP at all.
Can we please see what the commands are behind that?
The commands behind it is just a scatter plot.
Yeah, no, the pos equals plus 4.
Oh, that's just
Yeah, but I need to know what the commands
And because doing that for every single range or for every single master charge window would be ridiculous if you regularly work with atom prop data in Matlab. I've created Xrange in the Xrange editor, which I think most of you are familiar with. If you're not familiar with, you'll find it on my webpage and you'll find tutorials for it on there. So it does pretty much everything that the usual ranging program in either the commercial software or somewhere else does for you. And it just goes much faster than if you do everything by hand. But of course, always keep in mind you can do everything by hand as well, and that's handy if you do something that's very unusual. If you work, for example, with multiple hits, if you want to see different hit multiplicities, or if you work with the so-called sexy plots, so if you work with iron dissociations and things and you want to label things by hand, you can do that. You just need to do it by yourself. This is just examples. Don't work after that. This is just examples. But for standard visualization, I've created an export script that does everything, all of that for you. So provided you've got an Xrange file and provided you've got your POS file, it does everything for you. And if you go into the folder above, which is called General, there's one that says Create OBJ from POS and Xrange. And you just type that in. You just type that in and you hit enter, and it comes up with the dialogues for you.
Which do I need to import all of the folders that add path?
No, it does the path itself. So all you need to do is type that in. It adds all the paths you need by itself. Then you just choose your Xrange file. In the examples, there is one for this alloy. And once it's read that in, it will ask you for your POS file. You'll mark the POS file, and then you choose how you want to split it up. So if you want to split it up by atomic species, isotopic species, or ionic species, and usually we do atomic species, unless you do some fancy atom probe stuff, then you'd want isotopic or ionic, depending on what you want to work on. But usually if we actually analyze the material, we just split out by atomic. I don't know why it asks me twice. And now it's writing the different OBJ files. So for every single atomic species in there, it writes one OBJ file. And if we go into the example data now, if we look into the example data now, example, you'll see that we've got the folder here and it doesn't copy it into the folder. I don't know why. It should according to the Matlab script. And if you go in there, you'll see we'll have the data. So it's a very lengthy name, but it's got the it says where it came from. Doubles up on there a little bit. Sorry, I never went to fix up the scripts. But you can see you've got aluminium, boron, carbon, chromium, blah. And you've got one that's special, and that's the hull of the data set. And the hull of the data set is the so-called alpha hull or concave hull of the data set, which means it's sort of the hull that you would get if you used spheres of, in this case I've set it to have a radius of 5 nanometers, if you had spheres with 5 nanometers radius, and they would be tightly fitted to your data set. And having the boundary of the data set is a very, very important thing when I do analysis. And the rest is just simply the different atomic species. So we can go back into Blender now and find wherever
Hang on, we'll need to copy the files across for the people who find that.
it does work. And I just did it. What? Yeah. Yeah, you can go into the script and change the radius. But usually, so Andrew just asked what the thing is with the radius of the Alphahouse. You can change the radius, but if you look at an atom probe data set, the radius is pretty much always. It's not that much. It doesn't change much, right? If you look at the concavity at the bottom of an atom probe data set and at the bottom of an atom probe data set, it doesn't have a radius of 0.2 nanometers, and it's not going to have a radius of a couple of microns, right? So 5 nanometers is a pretty good value. If for some reason your hull would look completely weird, you'd go and do that. Yeah. Yeah. Well, you can create a new hull. You can always calculate a new hull. That's why we're using alpha hulls in this case, because an alpha hull can always be computed for a point cloud. Whereas the more modern, when I do my own reconstructions, I reconstruct a hull of the dataset along with the reconstruction, which makes it a lot prettier, because the alpha hull is not going to be a pretty triangulation. Because if you imagine you've got random atoms sort of randomly poking out of the surface, and that's going to form your surface. Anyway, so now we'll just need to find, where did I put this? It's documents.
I think who else has got the data?
Where did I put that? I think it might be on the desktop. Postdoc documents. There's supposed to be 2014 Atom Probe Blender Workshop, example data. And there we go. So I've got all that set up, and now I'll load in the boron because there's a little bit more boron. And if I click Import OBJ now, you can see we've got the boron in the data set. And right now you can see that it's in perspective view, but I think if you work with scientific data, it's always good to press 5 and go into orthographic view, because after all, that gives you a better view on what the whole thing looks like. I mean, you can tell the difference, right? And this is the item prop data. And as the next step, we'll move the camera. So we'll go and grab the camera and move it somewhere where we can actually see a lot. And there we go. If you don't have a camera in your scene because you've deleted it, then you add the camera by just right-click by Shift A and add camera. You can also have multiple cameras in your scene, and that helps you if you want to have multiple perspectives, but you don't want to move your camera because you might want to, usually you always want to keep your file in a way that you can always repeat a render, because you create a render, you write your paper, and then you think, okay, I want a different color, I want a different this, I want a different that. I can easily just go back and then just change whatever you want to change and re-render. So if you use different perspectives, use more than one camera. And if you do that, so Shift A, camera, so the second camera is now at a sort of weird position. But if you want to set that one to as the active camera, then you go Control 0, and then the camera, whatever camera you picked, is the active camera. I'll just delete the second one, and then the first one will be the active camera again. Alright, so who's got problems with loading data in, and what is the issue? Okay, Barbara. Okay, so something's not quite right with the file. Did he? Okay, has someone done it successfully? So Anna, you've got the data in Blender now. No, it just okay. So the exports, there's nothing wrong with the export script. Just I have no idea what went wrong with Barbara. Alright, I'll just go and make the camera a little bigger, because this actually, the Blender unit is supposed to be meters. So right now our data set is something like 80 meters, which is an unusually large object. But if we want to keep our camera in size proportion, we'll just make it 5 Blender units, so we can always see. It's got a decent relation with in terms of size. And the other next thing, while the other people are trying to load in the data, I'll just do a few things that you can go and look up later that are not 100% necessary. And one thing is, if you go into N, which gives you the properties panel on here, you'll see the size of your object. So you can see it's 36 times 34 times 28. What I want to have is a cube for the later visualization to be the bounding box of that. So I'll just go and snap my cursor to the center, because where the cursor is where it puts the objects. So cursor to center, and go add mesh cube. And then next go into edit mode and move the cube down -1 Blender units, so that the top face of the cube is where the origin is. And then I go outside and I'll make it 40 times 40 times whatever height. So we'll make it the dimensions 40 times 40 times. Is that about right? No, it's too big. No, that's actually pretty much right. 40 times 40 times no, maybe not 60, 30. That's just a bounding box for visualization data. And that's just so when we do the render, we can say in our figure, when we create a figure for publication, we'll say, okay, this thing is, the bounding box is x times x times x nanometers, and this is always something very handy. And as I said before, this is now a solid cube. We don't want a solid cube, we want a wireframe. So I'll go into the modifiers and say, give us a wireframe modifier, and the thickness as it is I think pretty good already. All right. So just maybe now, if you want to move your camera around the same way you move the viewport around, you just go here. So this comes up with N, and click lock camera to view, and then you can go and move it around, move the camera around a bit. Maybe things are a bit obstructed. And when we work with atom prop data, because compared to the dimensions of what we usually do in Blender, it's fairly large, you'll see some of it disappearing. And that's because the camera has got a clipping distance. So whenever this clipping is happening, you need to go here into the camera and set the clipping distance to a larger distance to what it is right now. So 500 is usually plenty. And here we go. If I render it now, you'll see we've got the wireframe here. We don't have, I'm sorry, I've still got Freestyle on. That's why we get the lines here. I'll just switch Freestyle off. We've got the wireframe, and of course it didn't render any of the atoms that we actually want to render, unless we go and render the image. Oh no, it doesn't. Okay, never tried that before. Interesting. Oh, because we haven't got it selected. If we select it and render it, okay, it doesn't. Anyway, no, we're in object. Maybe because we're in object mode. I've done renders with the OpenGL this way. Anyway, forgot how. So we need to have actual objects that are representing our atoms. And the way we do that is we snap, in case the cursor is moved, we snap the cursor to the center, so that at 0, 0, 0, or you snap the cursor to the object. You actually need to put the sphere that you're using for visualization of your atoms to the origin of the object that's representing your atoms, because you might have more than one set of atoms in your view. I don't usually do that. I render, carbon and in an image, and then I render nitrogen in an image or whatever. But maybe you want to have, two side by side or whatever. Then then you need to do that. But try to stick with 0 as the origin. And we go and add mesh icosphere. Of course, you could use a different object as well. But icosphere is the most common one. And you go T for the toolbar. We remove N. And here you can see the size. Subdivisions means what the resolution of the sphere is, so how many faces it will have. 2 is going to be plenty. If you want to crank it up later, go and give it a subdivision surface modifier. And the size, usually atoms are sort of 0.2 nanometers in size, so that's usually pretty decent size. Of course, that's pretty small now, but you can see the sphere. We've got a small sphere here, icosphere, with flat shading. We want the shading to be that part has. So we want the shading to be interpolated. So if you click smooth, you can see it looks more sphere-like. If you go flat, looks like the actual polygons. Anyway, so this is the basis for a visualization. Get rid of the toolbar, and now we're actually going to go and let's call it. I think it was carbon that we imported. Well, let's go and call this one. Oh no, boron. Let's just call it boron. Makes it easier. And the icosphere is going to be called boron atom. And the boron atom is going to be parented to the boron mesh. So this is the boron mesh. This is our atomic positions. And the boron atom is going to be parented to it. And what that means is just you take the boron atom and you drop it onto the boron. And now you can see it's a child of the boron. And it, because that's how we're going to visualize the atoms. Wait for the next step, okay? So we've made it a child of the boron. And now we go and click on the boron and click vertex duplication. So the icosphere as a child of the boron is now copied onto every vertex of the boron, and that's exactly what we want. Now we've got the we've got it as the proper distribution, right? So now all our atoms are visualized. So that's the first way of visualizing it. I'll show you another one. And next step you do is you give it a material, just like we did before. We give it a diffuse color. Boron is, in my view, boron is blue. And that makes it actually ready for render. So now you can see that the boron doesn't have a color. Why does the boron not have a color? It should have a color. That's a bit odd. Because it's too bright, it's all white. Because we've got the ambient occlusion still going here. Sorry, my bad. And now it's all black because we don't have any color. But as we said before, we're going to be mostly working without lighting. So just click Shadeless, and then go and render it out. And is it still set to black and white? Output. I know, RGBA, that's all fine. Freestyle's off. Alright, that's what happens if you try to demonstrate things. Because that actually, that's why we're here, so we don't just learn how to use it, but also how to troubleshoot, I suppose. Did I turn anything on that I should have not turned on? What? Oh, yeah, sorry, I gave the material to the boron and not the boron atom, of course. My bad. So now we made the boron the parent mesh with the material, but of course it doesn't make any sense. So if you just click here, you'll have a list of the materials, and we'll just click that one. We'll rename it boron material. So in case you had multiple datasets with boron, you just reuse it. You can actually load that material into different Blender datasets as well, into different Blender files as well. So I usually have one stash of materials, and whenever I render a new dataset, I'll just load all the materials for the different species over. And now it's all blue, and now we've got our atoms there, and with the bounding box and everything, and that's a pretty good start for a render, I'd say. So the other way of visualizing your data with Blender is using a halo material, which means we're rendering the mesh out directly without the vertex duplication, which is a faster way, and sometimes I consider it, especially if you want to make it look very two-dimensional. So if you do slices out of material that is not supposed to look very three-dimensional, I consider it a much better option. I think in one of the recent papers I've used that. So this is actually where's the oh, come on. So this is actually done with the halo material. So if you want to give it sort of a cross-sectional flat appearance, I consider that a better option. If you want to make it look very plastic, you do it the way we just did it with the spheres. If you want to look it more, make it look more like this, then you use the halo material. And the way you go about that is, first of all, you get rid of the drag and drop parenting, so no more parent. You go back into the material, you remove that material and create a new one. Sorry, we just created a material slot and not a material. Don't worry about the subtleties, just click on new material, and we'll make it a halo material, and with a hardness of 0 and the size 0.2 again. It's going to have a texture to it. We can do it without texture, but it doesn't look as nice. Oh, it's got the. Sorry, I'll just get rid of that. I'll move it onto the second layer. Alright, everything's there. Oh no, I've moved you. What's happening in the second? Okay.
Undo any of these operations, so you do Control Z
Yeah.
or Command Z or whatever.
Yeah, Control Z, yeah. Yeah, Control Z is always your friend. But also, whenever you're working with Blender, work with modifiers and things as much as possible so that everything you do is as reversible as possible at any time. So, why are we not getting anything with the halo material? That's a bit odd. Because it's not shaded. No. No, the alpha is 1, so it's not transparent. Anyway, usually you'd have a texture as well. And the texture panel is here. And I'll give it a new texture. And the texture type is image or movie. And you open one. And I've got some pre-made ones which are just white circles that I've created in, or black circles and white interiors that I've created in Illustrator. It's not very hard to do. Saved it on my desktop. Usually I've got my standard one that I'll open here. You can see that, show alpha. So our atom is rendered as this. So it just puts this image wherever there's an atom. And it's still not rendering them out. We'll eventually find out why it's not doing that. It's good that you're all here. And the next thing is influence color, influence alpha, and multiply. Because otherwise, so multiply means that we get a black ring, whatever color we put in the middle, and nothing outside. And that's everything here. Go back into materials panel. What is the issue here? It's not the size, they're not too small. That would have been an odd mistake. Let's see. Alpha, we'll give it a color. Oh, standard is mistake. We still got the vertex duplication switched on. I need to switch the vertex duplication off because otherwise it doesn't think it can render the object. It thinks the object is just a parent object for a vertex duplication. Got rid of the vertex duplication. Now we render it and we've got our boron atoms. Yeah, the resolution, if we would render at a higher resolution or whatever, it would look a bit nicer. I'll just make them large so that you can see what it would look like. Right? But you've got your individual atoms now here. And it can, of course, this is a very large data set. It's a large data set. Usually if you have 10 by 10 nanometer cubes where you're showing details, that's a much better effect to use. But anyway, that's the other way of visualizing your atom probe data. And now,
Export as a SVG or vector graphic.
So vector graphics are not you can't render a vector graphics in a traditional sense because that's not what rendering is. Rendering means you're calculating pixels. But Freestyle from the next version on will actually have SVG export. So you remember we had Freestyle before, we had the solid lines and the dashed lines. You can actually export those into SVG. And that will actually be a very, very handy thing for us because then you'll just render every atom as a blob and you can export everything as an SVG, which gives you a lot of options in terms of editing and getting rid of certain aspects of it and so on and so forth. So yeah, that's the visualization. So we've already gotten this is in terms of visualizing your data for a publication. That's already most of what you need. And the next thing that you would actually need is animation. So trying to animate what you do. One last thing I'm gonna actually cover is camera settings. So right now the camera that we have is a perspective camera with a focal length of 35 millimeters. Which sort of gives you the cool 3D effect. I think that's a good thing for a presentation, but I think it's a bad thing for a publication. Because in a publication, you don't want to distract from your data through any fancy visual effects. In a presentation, you can get away with it a bit more. In a publication, you shouldn't do that. And you'd go to orthographic and set it to an appropriate scale. And most of all, I'll move the camera somewhere. Most of all, set it to a round number and leave that for this scene always the same, so that you know whenever you load your image into Illustrator or whatever, when you create your figure, you know that this edge is exactly 60 nanometers. So it's going to be very easy to create a micron bar or something like that in your publication. And we're not going to use any of the more fancy options. So if you go and render it out now, you get the orthographic effect, and that's probably a little bit better for a publication. The only thing is, this is maybe a little for a grain boundary. You'll see the grain boundary a bit better if you do it this way. And so much for the visualization. Well, maybe we've made that a little bit long, so we can make the size of the camera a bit shorter. So, next thing that we're going to do is simply animate the camera. So if you want to animate, you usually do the stuff that Iris has, where it spins everything by 360 degrees. What we're going to do is not spin the data. We're going to move the camera rather than the data. That's a better way of doing it. And we're going to do it the complete way. So I'm going to show you how to set up a rig for that, just because that's the proper way of doing it, and it gives you full control of animations. What that means is we're going to have a target for the camera, and we're going to move the target for the camera rather than the camera itself. Because what that means is we can use constraints for the camera, so it will always point to exactly where we want it to point, and we can always rotate it just with this one control object, and it can make very nice animations in no time at all. And such a control object is usually an empty object. So just go empty, plane axis, and it's right there. The only thing with the plane axis, we'll make it a little bit larger. We'll make them 20, so you can see that 20 nanometers large now. And we probably grab it down Z. So if you go grab and then Z, then it only moves it around Z, and we'll move it, so our main attention is going to be the grain boundary itself, so that's where we're going to move our target. And now we'll go and parent the camera to the empty. So drag and drop it again, because now if I go and rotate this empty object, the camera is going to rotate along with it. And this way it's very easy to make an animation. What else did I want to do? Oh yeah, rename the empty and rename it camera target. So this is our camera target. And we'll go and rotate it by 360 degrees. And for that, we're gonna also use the timeline again. So remember, we had the timeline here before, so it just... Oh, sorry, I didn't show you how to split the view. So you go here into the corner and just drag down the corner, splits the view, and change it to timeline. Get a little bit larger maybe. And scroll a bit to the right. Sorry, it's a bit crammed on the screen. Unfortunately, usually I have better resolution than that. And now we have the playhead again and everything. and we can do the animation. If you think in a data set fully spinning, usually 4 seconds is good for that. We've got 25 frames per second, so we're going to need 100 frames. We're going to need 100 frames for that. And we're in frame 1, and we'll go and in frame 1, we're going to insert we've clicked on the camera target, so this is the object, the active object, and we're going to press I, which comes up with insert keyframe, and we need a rotation keyframe. So a lot of people have the habit to use location, rotation, scale keyframes for everything. This just leads to a very cluttered motion curves. Later you'll see what a motion curve is. So if you only want to animate rotation, just click rotation. If you only want to animate what the location of the object is, just click location. So we've inserted a rotation keyframe, and we'll go to frame 100, or just click to the right because it's the last frame. And you'll see we'll change the Z rotation and change the Z rotation to 360 degrees. And if you just hover above it, you can click I as well, and it inserts a rotation keyframe for whatever, it inserts a keyframe for whatever you're hovering above. So you can also do that for renderability, or you can use that for any property at all. And now you can see we've got a camera that rotates around in 4 seconds. But what you also notice is that it starts out and then speeds up and then slows down again. Which, of course, if you play that on as a loop, which you would usually do, it looks really weird. And that's the reason. The reason for that is the handles of the animation, and you can change that by going into animation layout here. So we were in the default layout. Now we're going into animation, and you've got the different F curves here. So the F curves are the motion curves. We're not gonna need the dope sheet yet. And you can see here we've got the camera rotation. That's actually the only curve that exists, and we only need the blue one. That's the Z rotation. It's the only one that's there anyway. And what we do is we'll go and click all. So we've marked all of the different, so you can see within whatever, how many frames we had, it went from 0 to 360. So that's our animation. And if we marked all and click V, we set the handle type to vector, so it changes from sorry, I'll just zoom in here. I know. So what used to be what was a round line. So if you go and click to free, all, and go to aligned, it's round. No, automatic, it's round. It's rounded out with the speeding up and slowing down. And if you go to vector, then it's nicely doing the animation. And now we can just go back to default, and you'll see, okay, maybe 4 seconds for a full rotation was a bit much, a bit short. So we want to change that. I'll make it 8 seconds. And while we do that is we'll set the end to 200 frames instead of 100 frames. And we'll just go and change the location of the keyframe, which means we go back into animation and go into the dope sheet. It's called dope sheet. Dope sheet means where the keyframes are. So you can move the keyframes. And we'll grab the keyframe that used to be at 100 and grab it by 100. Or you can just go G and move it around. Right? I'll move it to 200 and go back to default. And now we've got it much slower. And we've got our animation here, our rotation animation. You can animate pretty much anything. You can animate sizes, shapes, locations, blah blah blah, and so on and so forth. But I think that's the most common animation you'll probably do for your Atom Probe data. And this is now perfectly ready for being looped. In terms of render times, so we'll just go and set it to QuickTime with JPEG encoding, and you'll see that if we do it with the halo material that I showed you before, that it actually renders at a reasonably quick pace as well.
What's all that orange stuff?
The orange stuff is the actual render tiles. So each thread on your computer renders one tile. If you render something a little bit more complex, you'll actually see them, like it will render one tile and then move to the next tile and render the next tile.
But that won't show up on the final image.
No, it won't show up in the final image. And that's it. It's rendered. So if I go into the terminal, and go into the temp folder, you'll see the movies here. That's just QuickTime plays it back with a black background. It's actually rendered out with a transparent background, I hope. If I click, yeah, it's rendered out with a transparent background. So for movies, very often the transparent background is not good because you never know what player is going to play it and whether the programmers of that player thought it's good to have a white or good to have a black background or have a gray background or whatever. So you'll just go into the world setting and make the color the sky color white, and go back into what I showed before, into the shading, and go sky. And now if you render the animation, you'll see it comes with a white background, just the way it usually want it. Of course, you can render it with a black background, but then would use a white box. Doesn't make any difference in terms of performance. All right, and that's the basics of animation. And that's, I think, in terms of visualization, we've already covered quite a lot. So if Vivara actually produces a nice importer script where you can use range files and pos files straight away, you can see using this rather than Iris to visualize your data is not actually a big jump. It's not something that's gonna, it's gonna throw you into the cold water and it's gonna take you years to figure out. It's something that you'd be able to do pretty much straight away. All right. There we go. That's our animation that we've just created of a grain boundary rotating around in a box. And that was it for visual. Did you have anything? No, that was actually everything we wanted for the visualization. All right, good. So I'll close the first video, and that's it for the first part.
Thanks, Peter.
Thanks.
So I think we should reconvene in terms of the part 2.
Yep.
Like,